Okay, so in summary of what we said so far anyway, in each case, the element being oxidized loses one or more electrons to the element being reduced, and the element being reduced gains one or more electrons from the element being oxidized. In other words, the processes always have to occur together. It's a fact, though, that the transfer of electrons isn't always complete or total. And because the total transfer of electrons would result in ionization, whereas sometimes the transfer of electrons is only partial and results in an unequal sharing of electrons. In other words, a covalent bond. And an example of that would be the reaction between hydrogen and chlorine to form hydrogen chloride. Okay, try and make an arrow here. Hydrogen chloride. Hydrogen chloride, if it's a gas, and it probably would be if you're making it from hydrogen gas and chlorine gas, is a covalently bonded compound. And so in other words, it's not ionic. It'll ionize if you put it in water, but as long as it's an intact molecule, it does not consist of ions. It actually consists of hydrogen covalently bonded to chlorine, and the chlorine pulls the electrons closer to itself, but it can't take them completely away from the hydrogen. And so that is an unequal sharing, or in other words, a polar covalent bond. So in this case, the charge on the hydrogen would not be a complete +1, and the charge on the chlorine would not be a complete -1. In reality, they would be partial charges. The hydrogen might be, plus 0.4, and the chlorine might be negative 0.4, rather than +1 and -1. And that brings us to the concept of oxidation states. Oxidation states are sort of a bookkeeping method for keeping track of where the electrons are and where they go, and where they end up. And sometimes oxidation states are real charges, and sometimes they are not. So oxidation states are real charges if ionic compounds are involved, or they can be hypothetical. And that's in the case of molecular compounds. And they're basically used for bookkeeping purposes to sort of keep an eye on where the electrons are and where they're going. And so, as I was saying, in molecular compounds, the actual charges present on the atoms will not be whole numbers, but we often represent them as whole numbers for convenience. Because while we know that those charges are not whole numbers, we don't know what they actually are. So what are you going to write? We know that the charges in HCl, the charge on the hydrogen is not a full +1, and the charge on the chlorine is not a full -1, but we don't know what they actually are. And they might be different for different compounds, and so finding out what the charges really are and writing those numbers, that would be pretty difficult. So for convenience, we represent them as if they were whole numbers. In this case, the shared electrons are assigned to the nonmetal atom that has a stronger attraction for them. Okay, so we're basically we're in a situation where we assume or we act as if the compound is ionic, even though we realize that it isn't. So in the case of HCl, we would assign the hydrogen an oxidation state of +1 and the chloride an oxidation state of -1, even though we know that this is not an ionic compound. And when it's in the gas state, not dissolved in water, it's not actually ionized. Okay, so we've kind of, we just assign full charges for convenience. And that charge, that hypothetical charge, is known as an oxidation state. You can also think of an oxidation state as the charge an atom would have if all the shared electrons were assigned to the atom with the greater attraction. Okay, so for hydrogen chloride, the molecule basically consists of hydrogen sharing a bond with chlorine, and that bond consists of 2 electrons. And so you can represent the 2 electrons as 2 dots between the H and the Cl. The shared electrons, and there are 2 of them, are pulled more strongly by the chlorine. And so hydrogen basically loses its 1 electron. And so the hydrogen is assigned an oxidation state of +1. And chlorine on the other hand, gains 1 electron, but gains in quotation marks, because it's really just pulling them closer, but we're acting as if it has taken them completely away for convenience. So the chlorine gains, in quotation marks, 1 electron from hydrogen. And so chlorine's oxidation state is given as -1. When we did charges on ions, the convention was to put the sign after the number. But actually, the convention with oxidation states with these hypothetical charges is the other way around. So we write this as +1 and -1 instead of 1 plus and 1 minus. Okay, so there are some rules for assigning oxidation states, which we can go over. That'll help clarify things, hopefully. So the rules for assigning oxidation states. And there might be some cases where two of these rules conflict with each other. And if that's the case, go with the first rule, or the one that has the lowest number. Rule number 1 is that the oxidation state of an atom of any free element would be 0. So, free elements are neutral, so there's no charge. Rule number 2 the oxidation state of any ion is equal to the charge on the ion. Okay, so for example, if you have a sodium plus ion, then the oxidation state for that ion is +1. Seems pretty obvious. Rule number 3 is the total of all of the oxidation states of the atoms in a molecule have to add up to 0. Okay, so if you have something like, say, NaCl, the total oxidation states for sodium and chlorine in that molecule have to add up to 0, because that is a neutral compound with 0 charge overall, so the total charge has to be 0. If you're talking about a polyatomic ion now, the total oxidation state of all of the elements in the compound, or in the polyatomic ion rather, have to add up to the charge on the polyatomic ion. And so for an example, if you're talking about the sulfate ion, which has a -2 charge on it, then the total of all of the oxidation states of all of the atoms in that ion must add up to -2. So that makes sense, hopefully. Rule 4 is that metals have positive oxidation states in compounds. And the group 1A metals have oxidation states of +1. The group 2A metals have oxidation states of +2. Group 3A metals have a charge of +3. All right, number 5. In compounds, nonmetals are assigned oxidation states in a kind of hierarchy. And that hierarchy is directed by a property known as electronegativity. First of all, what electronegativity is an attraction for electrons within a bond. So some nonmetals have a stronger attraction for electrons within a bond than others do. But generally, all nonmetals have a fairly strong attraction for electrons within a bond. It's just that some are stronger than others. There are actually numbers assigned to electronegativity, so you can tell exactly how electronegative one atom is relative to another, but we don't really need to know that yet. We'll get into electronegativity in much more detail in the future. But for now, what we really need to know is what the trend in electronegativity is. And as you look at the periodic table, which looks something like this, the trend in electronegativity increases as you go up a group, and it also increases from left to right. The least electronegative element of all is way down in the lower left-hand corner, and that's francium, or cesium is the same in electronegativity. And the most electronegative element of all is fluorine in the upper right-hand corner of the periodic table. This trend leaves out the noble gases. They're kind of weird because they don't want to gain electrons and they don't want to lose electrons either. Most elements want to either gain electrons or lose electrons. Electronegativity means how much an element wants to gain electrons. Fluorine is the highest electronegativity of any element, meaning fluorine really, really, really wants to gain more electrons Francium and cesium have the lowest electronegativity, meaning they don't really want to gain more electrons at all. They'd really just as soon give away some of their electrons. Okay, so the trend is greater going up a group and going left to right. So in molecular compounds where you're dealing with nonmetals, the atom with the greater electronegativity the atom with the greater electronegativity gets to take what you might think of as its favorite charge. The favorite charge would be the charge that we were talking about when we talked about the characteristic charges that elements take. You know, the A group metals, the charges that they tend to take in compounds would be the group number. So sodium is in group 1, it's always +1 in all of its compounds. For the nonmetals, the favorite charge is the group number -8. So for example, fluorine is in group 7. Its favorite charge is 7 - 8, which is -1. Oxygen is in group 6. Its favorite charge is 6 - 8, which is -2, and so on. So the atom with the greater electronegativity takes its favorite charge, and the less electronegative element takes whatever charge it has to make the overall charge work out. Okay, so an example of that might be the compound OF2. OF2 involves oxygen and fluorine. Fluorine is the more electronegative element present, so fluorine gets to be its favorite charge, which is -1. Oxygen ends up being whatever it has to be to make the overall charge work out. Now, OF2 is a compound, so we know that the formula has to have 0 charge overall. And if each fluorine is -1, and there are 2 of them, that would mean that the fluorines together have to be -2. And there is a single oxygen to bring that total charge back up to 0. So the oxygen must be +2. So the oxygen, which normally likes to be -2, is actually ends up being +2 in this compound, because that's what it needs to be in order to make the overall charge work out. Fluorine is more electronegative, so it gets to be -1 like it always wants to be. And oxygen is basically left to fend for itself. And so that's how you can figure out the charges in a compound. There is also a table to help with assigning electronegative, oxidation states, where basically you can assign oxidation states based on the element. This is a hierarchical table, meaning that if 2 entries are in conflict, the higher entry takes precedence. Notice that that first entry up there is fluorine is -1, because that is actually always true. There are no exceptions to that. Fluorine is the most electronegative element of all, so even according to my rule up here, Fluorine always takes precedence over everything else and gets to take its favorite charge, which is -1. Hydrogen will be +1 with nonmetals, but -1 with metals. Oxygen, which is the second most electronegative element after fluorine, gets to be -2 unless fluorine is present. Then it has to fend for itself like it did in OF2. Elements in group 7A will generally be -1, except when combined with something above them in the list. Elements in group 6A will generally be -2 unless they're combined with something else above them in the list. And elements in group 5A will tend to have a charge of -3, again, unless they're combined with something above them in the list, and then they might have to be something else. So generally, the oxidation states of most nonmetals in a compound will depend on what else is present. Really, the only absolute is fluorine. Fluorine is always -1, but other nonmetals could be just about anything depending on what else is present. Okay. And a lot of times, you can assign the oxidation state to whatever element is most electronegative in the compound. But then for the other elements present, well, particularly if they're nonmetals, you often have to deduce what the other oxidation states are based on making the overall charge work out, like I did with OF2 just a minute ago. Also, the charges of transition metals will have to be worked out in order to make the overall charge work out, because transition metals can take multiple charges. We don't know which of those charges they're going to take in a compound just based on its formula. So you have to find out what it needs to be based on what other elements are present and what the overall charge is. So just as some examples, we can assign oxidation states to each atom of each element in the following examples. And we have a few examples here. Okay, so the first one is just chromium, just the element chromium. And if you've got just a neutral element, then the oxidation state is 0. The second one is the chromium +3 ion. And as we said, for monatomic ions, that is an ion that's formed from a single atom, the oxidation state is the charge on the ion. So chromium +3 has an oxidation state of +3. In CCl4, that's a compound. It involves carbon and chlorine. We know that being a neutral compound, it has to have 0 charge overall. And of the two elements present, carbon and chlorine, chlorine is the more electronegative because it's to the right of carbon in the periodic table. And so chlorine gets to take its favorite charge, which is group number -8. Chlorine is in group 7, so 7 minus 8 is -1. That means each chlorine in this compound is -1. Okay, but there are 4 of them. So that means the 4 chlorines together are -4, and there's only 1 carbon to bring that back up to a total of 0. So the carbon has to be +4. Okay, +4 minus 4 equals 0. So there's those. In D, that's SrBr2. Well, this one isn't too hard because SrBr2, strontium bromide, is an ionic compound. Strontium is a metal in group 2A, which means it's always going to have a charge of +2 in any of its compounds. Bromine is a nonmetal in group 7, and with a metal, it's always going to be -1. So that one wasn't really too difficult. E is SO3, the compound. SO3, in this case, is a neutral molecule, so it has 0 charge overall. It's made up entirely of nonmetals. Sulfur and oxygen are both nonmetals. Of the two of them, though, oxygen is above sulfur in the periodic table, which means oxygen is more electronegative than sulfur. So oxygen gets to take its favorite charge. It's in group 6, so its favorite charge is going to be 6 - 8 or -2. So oxygen gets to be -2 each, but there are 3 of them. That makes it -6 for the oxygens altogether. And there's only 1 sulfur to bring that -6 back up to 0. So that means the sulfur has to be +6. And indeed, that's what it is. And the last example would be the nitrate ion. Now, out of the, NO3 is involved, NO3 involves nothing but nonmetals, nitrogen and oxygen. Of the two of them, oxygen is to the right, which makes it more electronegative. And so oxygen gets to be -2, as it always is in all of its compounds, except when it's with fluorine. And that leaves nitrogen to fend for itself. If each oxygen is -2, and there are 3 of them, that makes -6 for the oxygens altogether. And nitrogen, there's only 1 nitrogen to bring that -6 up to -1. From -6 to -1 is a difference of +5. And there's only 1 nitrogen to share that charge, so that means nitrogen's got to be +5. And it is. Okay, so that's basically how you go about assigning the oxidation states. This 30 minutes or so right now, so I'm going to stop this segment and start with part D in a moment. So see you then. Bye.